online. Just a quick reminder here that if you do have questions online, please put those in the chat. I think we'll probably just save the questions till the end. We will have a little interaction. Thanks to Infinity, they brought a solar panel and some other things, microinverter, ground screws, so we can talk a little bit about some of the equipment that they use in their installations. Thank you very much to Northland Library for sending Katie to help us out. So she's been helping with promotion and the technology side. And then for what it's worth, I am a member of the Environmental Advisory Committee for McCandless. I'm also a professor at the University of Pittsburgh, mechanical engineering professor. And so anyway, I'll be giving the talk today. Going solar. So we're gonna kind of go through a few kind of big picture items, and then get into a little bit more nitty gritty of the solar panel installation and things like that. I'll talk a little bit about costs. For what it's worth, we will have I have a little Excel spreadsheet pro forma. Essentially, you can plug in some numbers and figure out approximately what kind of returns you have, return on investment. We could look at electricity rate over the 30-year lifespan, right? So I'll go ahead and we'll be emailing that out when the talk is over, so you'll have access to that. So like I said, we're going to be talking a little bit about power the sun, what we need to actually power the earth if we want to use all solar. Environmental impacts. So I think everyone kind of thinks bottom line right away, but I think one of the things we have to consider is the environmental impacts of not going solar versus going solar, right? There's also some health impacts. We'll talk briefly about that. And then we have some pretty positive solar trends recently. So we've seen a great reduction in the cost of solar. Unfortunately, lately with some of the shipping issues and supply chain issues, it's gone up a little bit. But the costs, I'll show you the costs have gone down drastically in the last decade or so. And then we'll start to work through solar, how solar works, and then residential solar systems. So as I mentioned, I'm a professor. I started my undergraduate at Duquesne University in physics. I went on for my bachelor's, master's, PhD at Pitt, and did some research in concentrated solar energy along the way. And then I was a professor at Robert Morris University, the mechanical engineering department, for about 9 years. I did some research in solar photovoltaics, life cycle assessment, alternative fuel, and so on. So now I'm a professor at Pitt, so I've been at Pitt since 2019. I'm the advising coordinator for the department, and I also teach courses in both mechanical engineering and we have a sustainability certificate for the students. So there we go. All right. So I'm not sure if any of you have ever seen this show, Deal or No Deal with Howie Mandel, but I'm gonna lay out a scenario here and see if you think that if you'd like to take this deal, right? So I got a great deal for you. I can sell you electricity that costs twice as much. It produces 100 times more greenhouse gases. The price will double every 30 years or so. Every once in a while, you might have a blackout, and you'll own nothing. You'll just continuously pay me. Would anyone like to sign up for that deal? Yeah, sign me up. But essentially,
radio.
Yeah, that's right. Exactly. Yeah. So if you think about it, double the price is relevant. It depends on how much you pay for your solar array, those kind of things. But really, what we're looking at is this is kind of utility system, right? This is the way utilities that we pay right now. We'll never have any equity in our home, right? We'll never have a steady electricity rate. Will always be increasing. Whereas if you build solar today, you can imagine your electricity rate is locked in place, right? We'll talk more about that. All right, so I am a professor, and I have to have some sort of a quiz somewhere along the line here. So my pop quiz is, does anyone know how long it takes the sun to shine on our planet to provide enough solar electricity for the entire year? So we got 4 options: 5 minutes, 1 hour, 3 weeks, or 2 months.
The entire planet?
Entire planet. So we can power the entire planet if we, obviously, you can't put panels on the entire planet, right? But hypothetically, if we were able to put panels on the side of the planet that's facing the sun for how long would it take to get the power to power all society?
5 minutes.
5 minutes, okay. Close. It's actually 1 hour. Yeah, so 1 hour, right? So it takes 1 hour to power the entire Earth, right? That's 22,000 terawatts. Terawatt is just, terawatt hours, right? That's just 22 trillion watt hours of electricity. So quite a bit. Another pop quiz here. How much area is needed for a solar array large enough to power the entire world? So if we had a solar array just sitting there, and it was, it was just sitting there powering, somehow you run cables to every city in the world. Hypothetically, right? What size do you think? We got Kansas, Texas, Australia, Brazil.
Australia.
Australia, okay.
I'll go with Texas.
Texas, all right. Well, the answer is Kansas, believe it or not. Yeah, so obviously these are estimates, and as you can imagine, electricity consumption will grow year after year. So, you'd have to grow your solar array. The other obvious thing is we're not going to run power lines from Kansas over to China or something like that. But the point here is we can power the entire world on a solar array that would be about 300 miles by 300 miles. So I think hopefully that puts into perspective that, I think there's this thought that we're going to have to cover every piece of land with solar in order to be able to power the world, and it's not true, right?
How much area is there out there now in solar?
Oh, I wouldn't know that. Yeah. We could get numbers on capacity, like solar capacity in the US and things like that. But yeah, I wouldn't know that. Yeah, good question. Yeah, so if we wanted to power the US, it would take about 120 miles by 120 miles square. Kansas isn't exactly a square, but the square miles work out. So this would power the US for about, whatever, let's say next 30 plus years. Costs around $4 trillion, which would be equivalent to about the US federal budget for a year. Okay, so anyway, just some kind of big picture ways to think of this. So power the entire world for 30 plus years for 1 year's annual budget of the US. So if we think about the environmental impacts of what happens when we use our electricity, I want you to think about ways that you use electricity today. Right? So for instance, flipping on a light switch or something like that. So think about where the electricity came from. Maybe your house, maybe you purchase a power purchase agreement with Green Mountain Energy. Maybe you just use the utility electricity. And then think about what environmental effects are occurring because of that consumption. Does anyone want to share out their energy with what they did to consume some energy, electricity, let's say?
Hair dryer.
Hair dryer, okay. Oh, that's a powerful one. It's like 500 watts or something like that. It's like running a microwave. Yeah, so your hair dryer. Okay, and then where did the energy or electricity come to power that? Where do you think it come from?
The line using the
That's what most people say, right? So yeah, typically it comes from utility company, in which case you have some mix of gas, coal, could be hydro, could be wind, could be nuclear, right? And then obviously we have solar in there too.
So what do you think, what's the most in our area here? What's, sorry, so we do have a nuclear plant not that far away.
Yeah.
But also, probably natural gas fired, I don't know if there are any coal fired places around.
So yeah, so coal fire has been dropping pretty drastically compared to natural gas. And so with the low prices of natural gas, I think recently there's been a lot more natural gas turbines come online. Lately though, the prices, last year or two, the prices have gone up quite a bit. So the electricity rates will continue to go up. One thing nice about nuclear, those plants continuously run for 50 plus years, right? Yeah, I would say the majority of our electricity here comes from natural gas. We do have some hydro also, but yeah, nuclear, coal, and natural
And
gas.
where's the hydro coming from?
Well, we have there's some hydro up northern Pennsylvania, and then there's some smaller hydro plants along the Allegheny. Yeah.
Okay.
So anyway, this is a general picture of the electricity consumption in the US, right? So you can see the majority of it is natural gas. I don't know how well you can see that, 39%, coal's 22%, nuclear is 19%, and renewables is 20%. So that renewables is mostly hydro still, right? So solar only makes up about 3% of the total. So, but that number has actually been increasing quite a bit. So when we think about our environmental impacts, we can think about the ways in which the energy is produced and then what we have to do to get it there, right? So you can imagine coal, we have to dig it out of a hillside or you know, it could be, you know, deep mine or something like that. With natural gas, we have to you know, drill wells, sometimes frack those wells, maintain those wells and piping and lines and everything there. And then we have our renewables. Obviously, we have to install solar and wind, and those are maintained, although operation maintenance is pretty minimal. But those are, you know, 20-year plus. Solar can be 30-year plus investments, right? So a higher initial investment, and then the investment is, you know, you basically maintain the facility, and you don't have to continuously increase or continuously provide fuel to that asset. So the average U.S. household consumes about 10,700 kilowatt hours of electricity annually, and that equates to almost 10,000 pounds of carbon dioxide per year. If we look at the exact same amount of consumption with a solar array, that would drop down to about 100 pounds, right? So we're looking at over a 99% reduction in the greenhouse gas emissions when looking at solar versus the typical electricity, the electricity mix that I'm showing there. So you might be asking why I have a light.
Why would solar consume any carbon?
Oh, yeah, good question.
Or, you know,
Yeah, good point, right? So it doesn't actually produce any emissions, right? While it's going, right? While it's running, absorbing photons. The emissions only come from the production, transportation, installation, that kind of thing. Does that make sense? Yeah. So you know, you can imagine if you're producing silicon, you have to use a whole bunch of heat to heat the quartz and get rid of the impurities, that kind of thing, right?
Mhm.
So all of the processing part, and so I didn't really go into detail here, but if you look in the middle, that's kind of the basis behind life cycle assessment. You can imagine you have some material extraction, like you have to take the silicon, purify it. You have different boron and phosphorus that goes into the silicon. You have aluminum and glass. Right? So all of that production, the production facility and that kind of thing. Yeah. So yeah, good point actually. So there's no continuous combustion of anything. You don't have to continuously fuel. And while the solar panels are there, there is no actual emissions, right? The emissions here are just strictly related to the production. Yeah, great point. So same thing here, right? So if we're looking at the environmental impacts, you look at the very top there, you'll see coal, right? So coal produces about 820 tons of carbon dioxide. You don't really have to worry about it's per gigawatt hour. It's just a large sum of electricity. But if you compare that to the exact same sum of electricity that's consumed by solar, you're looking at 5 tons, right? So the difference is 164 times the amount of greenhouse gas emissions, right? As we know, we have environmental concerns with greenhouse gas, global warming, and things like that, right? So now I know I'm specifically talking about greenhouse gas emissions, but there's also other emissions, right? So for specifically coal, there's times where mercury might be emitted in other different contaminants as well. The other thing to look at there is the natural gas, right? So natural gas produces about 490 tons versus 5. So it's about 100 to 1 greenhouse gas emission difference, right? And so this is the global values. The US values are a little bit different, but this would be the world values, right? To get an idea of what a kilowatt hour of electricity would look like, it would be equivalent to something like running your refrigerator for 2 hours, or if you had an LED light bulb, well, that's a 60-watt light bulb, so that would be more like an incandescent light bulb. If you had that on for 17 hours, LED TV, you run that for 10 hours, right?
I think your refrigerator's on,
Refrigerator's off.
so it's much less.
Well, this was from the world data, I think. So anyway, yeah. So it might depend on what kind of refrigerator you have. Yeah. So maybe there's more energy efficient ones.
I know that.
Yeah. So if we were to look at the CO2 emissions from consuming 1 kilowatt hour, you can imagine just let's say instead of running, let's say we have our TV on for 10 hours, we produce about 1.8 pounds of carbon dioxide and release that in the atmosphere if we were to burn coal. about 1.1 pounds natural gas, and solar is only about 0.01 pounds, right? So you can imagine huge difference in the amount of emissions per energy source. So the average US home has about 45 light bulbs. If they're all 60 watts, so for what it's worth, hopefully everyone here is converting from incandescent to LED by now, so maybe a little more efficient than this example. But if they're all 60 watt, you run those for about 4 hours and you produce about 10 pounds of carbon dioxide if you had burned coal. So that was the reason I brought this pink bucket. So this is about 10 pounds of carbon dioxide if you had all the lights on in your house with incandescent light bulbs for 4 hours, right? If you had solar panels on your roof and you did the exact same thing, you would have about 20 grams. So this is 20 little paper clips, right? So this is the mass of the amount of greenhouse gas emissions, the carbon dioxide that would be emitted versus obviously a much heavier amount, right? And then with that, as it goes into the atmosphere, the carbon dioxide takes up a huge volume, right? It's not near as dense as paint or anything like that. But so sometimes I get the question, well, what about all the waste from these solar panels, right? So these solar panels, after 30 years, you're going to have these solar panels. What are you going to do with them, right? And so the answer right now is there are companies working on recycling, and I'll talk a little bit more about some of the, at least some of the latest. But you know, you can recycle the aluminum. The panels themselves are 75% of the mass of the panel is actually glass, so you can recycle the glass. It's a little bit tricky to pull them apart because there's some plastic encapsulants, like EVA materials in there. But the silicon itself, I mean, we're talking about a wafer that's 0.5 millimeter thick, right? So as any good professor would do, I'm going to answer a question with a question. So what does the waste from the alternatives look like, right? So I can either start with, I have this 400 watt solar panel. How many watts is this, David? 380. 380, so pretty close, right? So let's just say I have this on my roof for 30 years and it's reached pretty close to its end of life. And I'm like, well, worst case scenario, I'm going to throw this into a landfill. Now there's better choices, but let's just say I do that, right? I got 40 pounds worth of materials in a landfill. Well, what are other ways that I can produce, what is it, 14,000 kilowatt hours of electricity? How else can I produce it? Coal and natural gas, right? Those are the two big ones, green nuclear and others that are a little bit cleaner. But if I were to look at natural gas, let's just start there. The amount of cubic feet necessary to produce 14,000 kilowatt hours, essentially the amount that this one panel would produce over 30 years, would be 104,000 cubic feet, right? So over 100,000 cubic feet of natural gas to produce the same amount of energy or electricity from a 40-pound solar panel, right? And that amounts to 3.5 tons of carbon dioxide over that length. If I were to look at coal, obviously coal's a little bit dirtier when it combusts, so we actually have 16,000 pounds of coal, right? So I can either throw a 40-pound solar array in the landfill, which I'm not saying we do that. I'm saying we do try to recycle those, right? But worst case scenario, if I had to throw a 40-pound solar array into solar panel into the landfill, it would be equivalent to replacing 16,000 pounds of coal, right? So sometimes I get this question and I say, well, what are we even talking about here? It's not even close, right? But yeah, so the other thing is researchers are working on recycling materials. You can imagine one of the hardest parts, if you look at this solar panel, you'll see there's a bunch of little contacts. Essentially, there's where the electrons can flow through. And so that's integrated into the silicon itself, right? So it's tricky. You can't just peel that right off, right? It's not that easy. So but researchers are looking at ways to recycle the silicon material, turn it into new solar panels. The average solar panel is right around 22% efficiency. And just recently, as of February 2022, there's a Fraunhofer Institute for Solar Energy Systems, and they were able to take an old solar panel, crush up the silicon, and repurpose it into a solar cell that reached 19%. So not too bad, right? And there's a lot of research being done in that area. So this is one of those situations where time will, we will solve that problem over time, right?
How do you calculate the efficiency of the solar panel? You
Oh,
say
yeah.
22%.
Oh, yeah.
What does that mean?
So it's called standard test conditions, right? There's these basically big machines that provide 1,000 watts per meter squared of solar radiation onto the surface. There's something called the atmospheric mass ratio. Anyway, they have these standard test conditions. They hit the panel with 1,000 watts per meter squared. And if the panel, for instance, produces 200 watts, right, per meter squared, then they're 20% efficient.
Yeah.
So for what it's worth, though, you can imagine if I have a panel out there and it's a cloudy day, I'm not going to produce as much, right? It doesn't mean that the efficiency changes. It just means that the panel itself is just not receiving enough photon. Yeah, that's right. Yeah.
And what causes solar panels to reach end of life? What happens? Is there oxidation of the components or like after a certain amount of time, what happens?
Yeah, good question. I would imagine there'd be some degradation from the UV rays. There is some polymers, so there's an EVA a sealant material to keep all the elements off of there. So I don't know, David, do you have any better answer for that?
Yeah, just general age, light degradation, you're right, UV rays hitting the same thing, just kind of think of it as erosion from light. If it's in sun for 30 years,
That's right.
we usually model about a 0.5% efficiency loss per year.
Yeah.
And usually panel manufacturers will give you a warranty on after X years, it'll still be at this percentage of its brand new efficiency, which you can track.
Yeah, so when you buy a panel, a lot of panels are manufacturer warranty of 25 years, right? So they're telling you it's going to last for 25 years. And then they'll warrant that you are going to, and I think it's usually around 90% after year 20. Does that sound right?
It varies.
It varies.
How much do you want to spend, I guess? There's more premium panels you can get to be more efficient over time.
So what they'll tell you is your panel is going to reduce in efficiency, you know that, but it's going to reduce efficiency over the next 20 years by 10%, and we're going to guarantee that to you, right? So yeah, there is some degradation. It's not a whole lot. 0.5% a year is a pretty good estimate. Yeah, good question. So here's a look at just sort of, and I know you can't see this because I can barely see it, but the highlighted the highlighted area at the very top, there's 359. And what that's telling us is it's the dollars per megawatt hour, right? So megawatt hour is, if you divide that number by 1,000, you would end up getting your cost per kilowatt hour. I don't know if you guys inspect your electric bill, but it's probably somewhere around 10 to 12 cents or something like that for your electric bill. That would be 39 cents, right? I don't think many people want to spend 39 cents on electricity, but you'll notice that was 2009. 2019, we're down to $40. So a 90% decrease, right? And so that $40 would be like 4 cents per kilowatt hour, right? And so that's obviously a huge reduction in cost, right? So this would be utility scale. This is again a number from the world data. But the point here is the cost of electricity from solar has dropped dramatically in the last 10 years, right? If we look at the installed capacity, so with that drop in price, you can imagine people start thinking, especially developers, utility companies, hey, I want to start investing in this because I can produce electricity dirt cheap and sell it on the grid, right? And so you can imagine that increases the amount of installations. So that little donut shape there is showing the electricity, the renewables, that renewables made up the newly installed US electricity capacity, generation capacity, over about 70%. So I don't know how well you can see that, but the wind is 31%, solar is 39%. You can see natural gas is still in there, but the cost of renewables has dropped so drastically, and we're not talking about wind today, but wind has dropped very drastic, quite a bit as well. Not as drastic as solar, but yeah, the costs have dropped significantly. One of the considerations when we think about solar is the land use. We said the size of Kansas, right? But when we look at land use, we're not going to be putting, we can put solar panels on a roof, but a utility scale plant typically need a lot of land space. So you can imagine farmland is typically used in certain rural areas and things. So one of the concerns is, hey, we're going to replace all of our farmland with solar panels. But what a lot of researchers are doing, and actually we're starting to see these pop up, definitely in Europe, we've had a few in the States now. They're called agrivoltaics, and all it means is you take your panels, and instead of having them, 2 feet off the ground to about 8 feet off the ground, where they're, let's say, closer, you basically raise those up about another 8 feet, and it's almost like a canopy, right? Which provides some shading, so certain plants grow better under the shaded environment, It actually also will trap in some of the moisture. So there's some advantageous qualities to these agrivoltaics systems. So we can actually combine both agriculture and PV together. And one of the other kickbacks here is, as you can imagine, I don't know if anyone here has been a farmer. I'm not a farmer, but my understanding is that there are certain seasons, if you get drought or flooding or something like that, where, if your crop goes bad, if the market prices vary too much, you can have very variable income, right? With solar, you have a steady income no matter what. And then from there, obviously your crops would be kind of, I don't know if you want to say icing on the cake, but it definitely helps to stabilize income for farmers. All right, so that was kind of big picture. I want to start to delve into solar panels. This is going to be a good short little video that kind of goes into how the solar panels are made, how they're doped with different elements, boron and phosphorus, how those create different positive and negative layers and cause electrons to flow. So it'll give us the basis, and then we'll start to hop into some real considerations when we're thinking about putting it on our home. Maybe I might have to turn up my volume, so hopefully we don't have any. Oh, we do have an echo. Well, we might have to skip the video, I think. I don't, do you have any suggestions?
Is the little symbol for the sound in the bottom left of the picture there, is that all the way as high as it can go?
Oh, yeah, the problem we're having is we have an echo with Zoom, so it's kind of reverberating
Can you
back.
turn the Zoom off? So you don't hear me?
Yeah, I'm actually muted. I'm not exactly sure what the reasoning is there. Anyway, basically the video kind of walks through the production of the panels. You can see there's negative and positive doped sides. So essentially you can imagine if the photon from the light hits on the negative side, the electron is pushed away from the negative side and wants to go to the positive side. And so all of those lines on there are meant to collect the electrons from that negative side, run it through a circuit such as the grid or your house or whatever panel box, and then the electron can then find its way back to the electron. It's called the electron hole on the bottom. So that's the basics there. And then it talks a little bit about sort of intertwining these solar arrays into a grid, right? We'll talk about the technology a little bit more here. So I'll just hop back into our presentation. So as I mentioned earlier, the solar panel itself, right, is made up of a bunch of different cells. Each one of the cells is about 0.5 volt. So you can imagine that's not a whole lot of power. That's why, well, this one actually, this one is this is a multi-crystalline, isn't it?
No, just all black or black.
Oh, so they must have square cells that are, okay, anyway. Yeah, so
You have to get real close.
yeah, you have to look really close. Typically, you have a whole bunch of cells that are wired in series and then also in parallel. And the goal there is to increase the voltage and the current, and that gives you more output power from each panel. You can imagine as you increase the surface area, you're going to have more power output. And as you mentioned earlier, you increase the efficiency, obviously you increase the power output too. So these cells are put into a module, and then obviously a module we can start to build out an array onto a rooftop or even ground mount. So now that we've kind of looked at the solar array and solar panels, we want to consider what we have to think through, some of the things we want to consider when we might want to go solar, right? I'm not sure how well you can see that. The bottom left is an image of my home, and so I kind of measured out the area that I was willing to take up with solar, right? So it's about 44 feet by 14 feet. The slope of my roof is about 37 degrees. And so when you think about the angle of your roof, The optimal angle's pretty close to the latitude. Our latitude here is 40. So my roof happened to be pretty darn close. Just because if it's not anywhere near 40, you know, flat roof or something like that, that's not a problem either. It's just you would produce a little bit less for the same amount of sunlight. Right? On the upper right-hand side, one thing you'll see so that's upper right-hand image is a picture of my house, and you can see I kind of put that little arrow facing north. What you'll notice is that the roof on the right side of the roof there is the back part of my house. And you'll notice that it's not facing due south, right? So that's actually facing, I believe it's 120 degrees, but essentially it's facing southeast. And so not ideal, right? So there's also, you can't really see it too well in this image, but there's also some shading from trees. So although my solar array was not perfect for this, I still wanted to move forward with it. And so I ended up building out my solar array 2 summers ago. And you know, we did some calculations to see what it would produce if it were facing south, kind of perfect conditions versus this. It's about 20% less, right? But you'll see it actually ends up getting pretty close to my annual consumption. So I'm a little under. So that means I still have to stay connected to the grid and still have to, no matter what, I would suggest staying connected to the grid unless you're willing to pay for the battery system, which can be a bit costly. But if you're interested in sort of having a self-sustaining system, you can go that way. So the other thing to consider, the obvious one maybe, and maybe David can tell me maybe, but the one that might be the biggest barrier is your roof age, right? You can imagine you don't want to put solar panels on a roof that the solar panels will last 30 years and your roof only has 5 years left, right? Because then you put them on, you got to take them off in a few years. It doesn't work out too well. So I don't know if you have a rule of thumb, but I would say typically less than 10-year-old roof would be what you'd want to focus on.
Definitely, yeah. The newer the better.
Yeah.
Especially if you have old 3-tab shingles, flat shingles, those are less ideal just because they're going to have a shorter lifetime than the newer architectural, more embossed, thicker shingles. But I mean, you would think that the shingles would last longer since they're getting less UV exposure from the sun and less water dripping down their aggregate. So
yeah.
we install on whatever the homeowner wants us to, but we would recommend, 15 to 10 years old would be about the oldest you would go.
Yeah.
Unless you plan in the future, if you're okay pulling panels off, and we do that too sometimes. We pull panels off before we put them back on.
So what are both of you be addressing solar shingles?
Oh, well, I won't be discussing solar shingles in the presentation, but do you sell those?
We have not.
Yeah.
We've not installed those. New, up and coming. I think that's pretty awesome.
Expenses, they're still significantly more than panels. Yeah.
And much less peak power. They're much less efficient and produce less electricity. But if they were to continue to be, or if their kind of scale increases and their power gets better, I think that's awesome.
Yeah.
But I don't know if we're there yet.
Yeah, right. I think the technology still needs a little maturity. Yeah, good question. Yeah, so you obviously, when you're looking at the roof, you want to look at the integrity of the roof also, right? You want to look at your roof rafters, and for what it's worth, solar panels, they're really not that heavy. You can pick this up. Dave brought this in himself, right? So about 3 or so pounds per square foot is the way to think of a panel. For what it's worth though, depending on your mounting point, the 40-pound panel might be mounted on 4 locations. So you kind of have to figure out exactly, it's not exactly evenly distributed. There's certain mounting points. But anyway, those are all things that, solar installers and, well, I'm a mechanical engineer, so I will preface this whole conversation with, I kind of priced out all of the solar panels, equipment myself, and I actually found the subcontractors to install it. So I went a little, not quite DIY, but maybe a little more DIY way, right? So I did a lot of, there's quite a bit of calculation, permitting issues and things like that you have to consider. One thing to consider is structural engineer, right? You might want to bring one in, make sure that your roof can handle the load, right? And they'll do some calculations for things like snow load and wind load and that kind of thing. So you think about your orientation, you think about your roof, and now you want to consider what power you consume in your home, right? So you can start to think about, do I want to try to produce 100% of all my power consumption through solar, right? And I know you probably can't see this very well, this is very small, but this is an actual image of my electricity bill, and I'll kind of talk through the different pieces here, so I know it's a very small text. So when we check our electric bill, we want to first take a look at our consumption. If you notice, sort of in the middle on the bottom there's a highlighted area. I consumed, this was a couple of years ago, 9,167 kilowatt hours throughout the year. So a little over 9,000 kilowatt hours. So that was my target. I was trying to produce as close as I could to that max, to that consumption value. Also, when you're looking at your electric bill, there's two things you want to evaluate or take a closer look at, is your generation costs. So in my case, they were my electricity generation. So the generator that I was paying, in this case, it was Energy Harbor. I don't know if you can see that, but they actually do renewables. So that's why I was paying 6.6 cents per kilowatt hour. And then my distribution charge was 5.2 cents, right? So you add those together, you get about 11.8 cents per kilowatt hour, right around 12 cents. So my overall annual electricity costs were right at a little over 1,000, so 1,082. So I was hoping to build out my system to consume as close to that 9,167 kilowatts as possible. The other thing you might want to consider, I don't know if anyone's interested in maybe purchasing a plug-in hybrid or an electric vehicle, or maybe if you switch from a gas to an electric dryer, or you switch to a instantaneous water heater, electric instantaneous water heater. You know, all those things you might want to consider when you're thinking about putting in your system. Because obviously you want to plan for that additional consumption. So from there, this might be a little beyond what anyone would have to do here, especially if you went with a solar installer. But I actually went through and I went through. There's a website called pvwatts.nrel.gov, and so it's produced by the National Renewable Energy Laboratory. You can input your location. For what it's worth, we'll send out the slides here. So there's a link at the bottom. Yeah, so I know you don't have to write down the link if you don't want to. But yeah, there's the link in the bottom right there. But yeah, you can put in location. You can put in the size of the system you want. You kind of have to figure out the roof space, or maybe you have a ground mount, whatever space you have available when you start to think about sizing your system. And then the tilt angle, azimuth. Azimuth just means if it's directly south, it's 180 degrees. If it's off, like I said, mine was southeast, it's 120 degrees, right? And then your electricity rate. And what it spits out for you is the most important number is the electricity produced per year, 11,747 kilowatt hours per year. Like I said, my orientation wasn't perfect. I had some shading, right? So that doesn't account for this in this. So it does actually account for orientation. It doesn't account for the shading side. So anyway, my electricity is a little more than 20% off of this number, like a little bit less. So this is, let's say, a very ideal case, right? And then we have to start thinking about, if we want to build out our solar array, we have to think about some of the major components that we have to consider. We've talked about a solar panel, right? Does anybody know what kind of electricity a solar panel produces?
DC.
The DC, right, yeah. So DC, direct current. And does your house use DC?
AC.
AC, right, yeah. So we need an inverter. We need to convert from DC current to AC. And we can do that. There are centralized inverters, right? And so in my case, I guess I can't. Oh, the laser won't work. Okay. The little box on the far right, the white box, it's about the size of a backpack. That's my inverter for my whole system. And then behind each panel, you'll see those little smaller boxes in the upper left corner of the image there. Those are called optimizers. So in my case, there's an optimizer behind each panel, and then that feeds into the inverter. Nowadays, I could have went with a micro inverter system as well, but micro inverter systems have become more and more popular. Essentially, you replace the big white backpack centralized inverter with a micro inverter behind each panel. So in that case, if let's just say a panel goes bad or something like that, you can pull off the one micro inverter and replace that. If my inverter goes bad, the whole system is down. All right, so there's a little bit of an advantage there. So you can kind of still run the rest of your array. Right?
But the way you did it is cheap.
Yeah, it's a little bit cheaper. It's actually not much of a difference. Yeah. If I had to do it over, I probably would have micro inverter. Yeah. I was trying to save a few bucks, and all said and done, it might have been, I don't know, less than 5% of my total cost. Yeah. But I'm happy with my system, but you know, if the inverter ever goes, I'm in a jam, I gotta hurry to replace it, so.
What do the optimizers do?
Oh, yeah, so optimizers, they take it, so you can imagine if I have that panel sitting in broad daylight, it's gonna produce a certain amount of power. If I have the exact same panel, like in my house, the bottom right corner gets quite a bit of shade in the afternoon, sorry, in the early morning. So, so that panel is gonna produce maybe half as much. Well, in the typical old school, like the older string combiner inverter systems, you would actually, the whole system, the overall production would go down with that shading. The optimizers, they take, and I don't know the exact, you know, what they do, but they basically, the point is they take the power, it's a max power point, so they basically produce as much power from each panel as possible. If you have them strung together and there was shading on one panel, it will reduce the overall power of the entire system. Yeah, so that's what they do. They basically produce the maximum power for each panel. Do I have that right, David?
Yeah, exactly.
Yeah, max power for each panel versus having to kind of lose power for the entire panel with just, or entire array, if just one panel is shaded or something like that. So, so one thing, so we go into the backpack, right, into the inverter, and then the green box next to it is nothing more than a big switch, AC, not a big switch, it's a small switch, but AC disconnect, not much different than the panel breakers that you have on your house. And then to the left of that is the meter. So you do have to have the utility come out and replace your meter with what's called a net meter. And that meter can spin forward and backward. It's actually digital, so I don't technically spinning anymore, but you know, it goes forward and backward, right? So you can imagine if during a sunny day, I'm producing significantly more electricity than I'm using. And so that gets sent back to the grid and is tallied as a credit to my account. And then at night, when I have my lights on, obviously, I'm using electricity and not producing, right? So that comes off my account. So it goes forward and backward. In fact, last month I got a credit. Usually my electric bill used to be right around $100 a month on average. I got a credit last month of $6. So I was proud of that. In fact, last summer I had a couple of months where I had like a $15 credit or $20 credit. So
Do they pay you the same rate that they charge you?
yeah, they do actually, just for the for the electricity and distribution costs, right? So yeah, so like that 11.8 cents, yeah, so that entire 11.8 cents is replaced with my electricity.
So they don't take off the distribution.
No, they don't. Yeah, so with the net metering, you actually get the entire amount back.
Is that gonna stay that way in PA? Or?
Well, don't ask me. You're voting. No, I'm just kidding. No. I think it will. I don't think there's. I don't think
some
so much
states do it
net
differently.
metering.
Yeah, there states do vary on the net metering laws, but we have our public utility commission that's pretty strong language against that. The utilities would love for that not to be the case,
Yes, right.
but I don't think it's gonna change.
I think the support is across all parties for net metering. I don't think there's any support.
Yeah, they buy and sell at the same rate, so you can think of it as like a 1-for-1, everything you generate, use, they transfer that out. If you were to overproduce over the whole year, let's say Tony's system produced like 15,000 kilowatt hours, that extra 5, he's only gonna get back at the generation.
Yeah, good point. Great point.
Okay.
Yeah.
And they
Yeah.
shore that up every year, so at June, let's say, he might get a check for, I don't know, $100 or something, but it's like at a discount for what it was throughout the year.
Yeah, I should have mentioned, great point. Yes, anything over your consumption, you only get the generation. Good point. Yeah, so I would only get 6.2 cents or whatever it was. Okay, so yeah, David, I don't know if you want to talk a little bit about Infinity and some of the projects you've done in the area.
Yeah.
And then, some of the equipment there.
Well, yeah, thank you, Tony, to have me. He's been consulting with us for a couple of years now and a great resource in McCandless. So great event. Thank you so much. With Infinity, we started in 2005 as a Penn State startup with the sole purpose to mitigate because of climate change. And we started by doing that as a construction company. We were building and still do build all electric net zero energy efficient homes in State College. And then we spun off a commercial energy management and engineering department that goes into hospitals and retrofits their equipment, helps them use less electricity. And then we have a solar division, and we've been installing solar across mostly central Pennsylvania and now in western Pennsylvania the past few years, since 2008. We've installed about, I don't know, upwards of 500 different systems, 5 megawatts installed. So just of the area, since we're in the North Hills, these are some recent projects we did. If you are getting your car detailed, I recommend Z-Bart of Wexford. They now have a solar powered car detailing shop. I got my car detailed there too as well. They have a pretty big array, 34 kW right on Route 19. Right below that, it's kind of hard to see there, but I would like to brag on our crew. That is incredibly difficult. That's a 12 pitch, multiple arrays, and we like went around their garage's skylights perfectly. And that's a really, really, really cool looking array in a residential area in Wexford. And then we have some ground mount arrays, one in Gibsonia and then a pretty big one in Allison Park. So just highlighting some, we work all over Western and Central Pennsylvania. This one thought I'd highlight some North Hills arrays over here. Yeah.
Cost difference, that's difference between mounting on a roof versus ground.
Yeah, ground's gonna be more because we have to dig a trench. You might see on the top right one, you have a large brown patch. That's us digging a foot deep trench to bury conduit. And the racking that holds up the panels is gonna be more. We have some racking over here, aluminum racking that goes on the roof, pretty light, pretty cheap, versus this is actually not for a roof, you can believe it. Versus this is one part of our steel racking. This is, instead of pouring concrete pylons, we just drill this into the ground. So the infrastructure behind the ground mount is gonna be more. I know it takes a little longer, it's a little more labor intensive. It's not too different, but I don't know, 15% more probably.
What does 11 kilowatt amount to in terms of a year?
Yeah, so that's when I say kilowatt there, that's the DC system size. So each panel is rated at 380 watts, and then that power rating over time is equals a watt hour, kilowatt hour. So it depends. I think for that person in particular, that's about 150% offset of what they use now. They are going to get an electric car in the future, and they're really cool, really environmentally focused, and they just want to put green energy back on the grid. So that's about a year and a half's worth of their usage, but it varies on what you're going to use versus what the size is.
If I can touch upon that.
Yeah, I'm not
PV
following.
watts. So what I had put in here, I know you can't see the numbers too well. This is actually a 10.1 kilowatt system, right? So this is what I did for my house. So this system probably produces, let's say, probably closer to 13,000 or so somewhere thereabouts, 13,000 kilowatt hours per year. Again, this is at a different angle, so maybe even a little bit more than that. But you can fool around with those numbers and actually figure out approximately how much your.
So the average house which consumes 10,700 would need somewhere around a 10 kilowatt.
Yeah, somewhere around
System.
there. That's right. Probably a little bit less, closer to a 9 or 8.5, probably. But,
Okay.
like I said, this isn't ideal. It's my roof isn't ideal.
Right. So that's,
Yeah. But that's probably a good kind of rule of thumb. Yeah.
Mentioning ideal, like we said, ground mount is more expensive, but you can point it directly south and you can tilt it at the perfect angle. So you're gonna produce, I don't know if it'll catch up entirely based on the cost difference, but you're gonna produce more on a ground mount, definitely. Versus like the Z-Bart of Wexford, it's pretty shallow pitch. It is facing south, but that's not gonna produce as much as those ground mounts are per panel.
Why couldn't you pitch those up,
You can, you used to do that, it's just more expensive racking, more labor to do that, and for what it costs to tilt them up, it's not worth it. It's pretty small amount you're gonna lose on tilts, as long as it's not tilting north, really, any flat to south. you're gonna be fine.
Yeah, it's actually not that much. The other thing you have to consider is the higher you tilt it, if the sun hits it, your shadow goes further back, right? So you can imagine you have to space the panels a little further apart. So you do lose some efficiency, but you can sort of squeeze, especially on a roof, flat roof, you might want to squeeze those panels in a little bit.
You'll see that. I've seen that. It's kind of funky looking to see them tilted up like that.
Yeah.
We wouldn't recommend that. Flush mounted is definitely.
And then the other thing, maybe beyond this conversation, but the additional wind load, right? You can imagine almost becomes a sail if you tilt it too high or whatever, but yeah.
Yeah, so the equipment I brought, this is a solar panel. If you come up really close, you can see the cells interchanged, but newer, later models are gonna have a black back sheet, just aesthetic, we just kind of think it looks cooler. I don't know if it produces anymore or
Exit on
different, but
screen share.
then on the back,
exit out?
we have our
Screen share so people
leads.
Can see what we show.
So all those silver things come together, this junction box. Then we have PV called MC4 connectors. And these are what your DC optimizers are gonna plug into, or what I brought was a microinverter. Little plastic box, and it gets plugged in to these, and then they're all plugged in together along the railing.
Is that the micro inverter?
Yeah, this is a
So
microinverter.
one panel has one micro inverter.
Yep. Yeah, so the advantage of that is you have
Each panel gets one.
you get panel level monitoring, so you could see they have this is from Enphase, which is by far and away the market leader. I don't know if any other manufacturer actually microinverters, but on their website, you can see your system, you can see, okay, my panel in the top left produced this today, or producing this right now. And then if it's not producing what it should, it'll alert you and us, like, hey, something's up with this one. It might be maybe a squirrel got in there or chewed something, or you should trim your tree. This one's getting too much shade, or the micro's down, and you can go replace it.
Do they home run back or they all daisy chain back?
I don't know.
Oh, okay.
I'm not sure. They're wired together in some sequence. I'm not the
I think we are daisy chain.
daisy chain.
Yeah, I don't think it's a home. Yeah, you got a home run for each panel. I don't think that's it, yeah. Yeah, I have, my optimizers for daisy chain, and I think that's.
Yeah. Okay.
Yeah, but like David was saying, that one of the nice things here is that you have a faulty inverter, right? That inverter is gonna directly convert DC to AC, so you have less line losses in the line itself, right? So now you have AC losses, AC going directly to your panel box. And then you also have, you have the opportunity to quickly change that out versus having to change out the inverter and losing the whole system for as long as it takes to ship, or whatever, order one, right?
So it's a shell of your system, like how do you know that this is?
Yes.
Yeah.
How do you know it's not working?
Yeah.
Yeah. So they're all connected to the internet, each one. So you can go on.
They
basically have an
IP address.
Yeah. So I can pull it up, I guess, but you can go on Enlighten and you can see a picture of your array, and you can see how many watts each panel is producing in that second. And if it's too low based on all the ones around it, it'll trigger an alert saying, hey, just check on this. And then Enphase will tell us, hey, Infinity, go check on that. Or it'll tell you, hey, call Infinity, check on that.
All right, let's say, if it's going to like a Generac home battery, the micro inverter is not going to convert it to AC, right? Because it has to go to the battery as DC.
I'm not sure what Generac, but Enphase makes their own battery product too, where
Like a home battery.
exactly, yep, it's called the IQ series batteries. And they convert twice. You have microinverter on the roof, convert to AC. The PV that's going to the battery is converted again by microinverters in the battery back to DC. It'll charge the battery and vice versa. So it's like a continuous loop. AC coupled battery is what it's called. A little inefficient, but very safe.
They're pretty,
Very,
chargers are very efficient.
and it's very safe compared to a DC coupled system. Having too much DC current going somewhere is full fire risk.
Yeah, good question. The monitoring is really, really cool. I mean, my system doesn't have the Enphase, but yeah, I can go on my phone and I can, in real time, I can see, certain panels are being shaded. Like I said, I have a whole section. I know they're gonna be shaded in the morning, right? So I can see them in real time. I can see daily production in real time, when it goes into monthly production, things like that. So
When it snowed, what did you see happen?
Freaks out.
Oh.
You're not producing anything.
Alert, sorry. Yeah, so, when it's snow covered, you're not producing anything, yeah. I don't, maybe the pitch of my roof is pretty steep, so I didn't have a ton of those days, but I did have some of them.
Yeah, it's not a huge issue. When it's snowing in January and February, the sun is low in the sky, so you're not missing much production. You're not going to produce much anyway. And when the sun comes back out, the panels are going to heat up quicker than your roof would, and it'll just slow it off. So it's not.
They don't have heaters in them for that?
They don't have heaters, no, but I mean, they do heat up certainly in the sun.
Yeah, my December production was probably about half of what it is, like right now in May. Yeah, so the production's quite a bit less in the winter months.
You're producing on a cloudy day too, obviously.
Not a lot, but you do.
You do produce on it.
Yeah, you can see outside, so there's photons come in somehow.
That's right, yeah, that's right. Yeah, so it's, what is it called, incident radiation? So you have the incident radiation or insolation hitting the surface, so that it would be, you have direct insolation if it's a sunny day, no clouds. But there's diffuse radiation, essentially when it hits the clouds, it's going in all different directions. So less of the photons make it to your panel, right? It might be shooting in all kinds of different directions versus being able to hit the panel directly. And obviously, if it hits the sun, the clouds, there's some absorption and things there too. Right? Yeah.
Also, maybe a boring part, some think this, they had a curious question about this, is the roof attachment method. How do you stick these things on your roof? And we drill holes in your roof, is how we do it, mainly your shingle roof. What we do is we would size or find where all the rafter trusses are. We would slip this sheet underneath the shingle, seal it on the bottom, seal it all on all edges, drill a hole. We have this foot that sits in this little fitting here, more sealant, lag bolt goes in the rafter, everything's watertight. And these are specifically designed to do two things: hold the solar panels on and not leak.
And those are warranted also.
Definitely, yeah, warranty for roof leaks. It sounds like it should be more of an issue than it is. It's really not an issue at all. And then what Tony did, I was looking for this product. We just were installing them right now, but he has a standing seam metal roof, which are pretty slick for solar because we don't need to drill in the roof. We just have these little clamps that just stick on the seams, tighten them. That's it, and that holds your L foot, and your rail sits on your L foot like that, and then all that really holds them down, at least for what we've been using, are these little, they're called UFO clamps. Slide them in the rail on the other side, and they just kind of seat on top, clamp it down, and just pressure fit in the whole thing.
So does it decrease the installation costs when we have a standing seam?
Yeah, not really. It's you have the same amount of attachments, and they're a little hard. It's like eerie when you're on a standing seam metal roof. It's kind of hard to keep things square because usually you have the shingle line to keep everything together. You have to like measure 3 times as you go down the road to make sure your rails are square. And then just the time to do it, getting into a certain torque rating.
Yeah, you have to torque them down.
First, it might be a little faster, but nothing we've quantified. About the same price for the
Shingles versus-
foot. Yeah, about the same price.
Funny story about my roof is I needed a new roof, so I started thinking about solar. There was an obvious connection there, and I thought to myself, well, I prefer to do the standing seam. So anyway, I got the standing seam roof installed a few months before the solar array, and I said I'm going to install the solar array myself. And let me tell you, my roof pitch was a 912, so it's 37 degrees. And my wife was with me. I climbed the ladder and I got up there, and I basically stuck onto the roof, and I couldn't move for about 10 minutes. Because, on a shingle roof, you have a little more traction. My feet were sliding and all, so I was freaking out, right? And after that, I said, no, I'll hire someone. But I did have an attempt. I was going to try to install it myself. The S5 clamps are really convenient.
Oh,
They
they're
basically
cool.
have two bolts that tight, the standing seam has a seam going up, and they basically clamp on the 2 bolts set into that seam, so there's no penetrations, which is nice. So if you ever wanted to take them off, there would be no penetrations to seal up or anything like that. But
This was last week. I was on a roof. You can just kind of see it clamped on the roof. That's Dwayne.
That's nice. Anyone else want to see this?
did you have anything else you wanted to talk about?
I can fly my drone if you want, but
I had a question. What about slate roofs?
yeah, it's tough.
That's doable, but yeah, the installation.
So it's tough because it's really hard to work on because you'll probably break them walking around. It's hard to drill through because you'll probably break them while you're drilling through it. So we, as a company, we do not install on slate roofs. It is just too big of a liability risk or loss. But the way to do it, I know a lot of companies on the coast and in the south, they have more like terracotta roofs. There's like, the way to do it is you would take the slate shingle out and you put in a composite like shingle roof mount built-in piece, and you put that in your roof instead of drilling into what is already existing. So it probably can be done. It's probably more expensive. So, but we don't have much experience with it, and we shy away from it.
Well, And any other questions or, yeah.
So if you have these solar panels on your roof, they're always producing power as long as there's sun outside.
Correct.
And you call a local fire company because you have a fire.
Yeah.
What do you do?
Yeah, so there's actually a recent building code that was passed specifically to address that in Pennsylvania. There's a shut off switch,
How long ago did that come out?
February 2022.
Okay, so it's that new.
Yeah, it's an international fire code that's been being adopted in different places as standard. What it was they increased mandatory setbacks from the ridge and from one side, like a clear pathway for them to vent it, for them to access roof and vent it. On top, which is a little, the rule is 18 inches from the ridge, 36 inches on the one side. So that was a little frustrating from like a design point of view, and if you want to maximize your roof, you're like, come on, I'm not putting panels there, but recently building code passed, four firemen that'll walk up there.
Okay, so that takes care of that, but if they still have to vent the roof because it's covered with panels
Mhm.
and they're producing electricity, I can tell you what most local fire companies do. And if you're looking to get these put on your roof, check with your insurance company before you do it. Because I can tell you, Shaler Fire Company, if you have a fire and you have panels on your roof, they will let it burn to the ground before they try to go in, because it's a liability, because it's producing electricity, they can't turn it off.
No, they
So-
can turn it off.
Yeah, you can turn it off. There's a nice switch that kills everything.
All over the
Okay, so when that
inverter.
turns it off, it turns all the inverters off?
Everything off, yep. And that's there for that reason, for fire, and if you need to work on the lines outside, utility lines, you would shut it off so you're not backfeeding the grid and shocking the guys on the pole.
Yeah.
So how long ago has that been in place? Because I know they just went through a safety training in the last 6 months to a year. And basically that's what they were told, that they will not go on a roof because they can't turn those panels off.
That's a shame, because the knife switch disconnects, always been there.
Yeah. But that knife switch kills it coming into the grid. But does that knife switch, like if I were to disconnect that panel from the cable coming over, it's still producing power if that inverter.
The circuit isn't closed, so power wouldn't go anywhere. Like the same if you turn a switch on, the load is, the supply is there, but the circuit's closed.
So really the
Or
question
circuit's
is,
open, so no power's gonna move anywhere.
no, but does a microinverter shut down
Yes.
if it doesn't see an AC sink source?
Yeah, so the microinverter, at least, they're grid interactive. They need to have grid power hitting them to turn on, and they know that sine wave on grid
Every
power.
one of those optimizers I showed you will not power anything unless it sees that centralized inverter, which has a disconnect on top of the other disconnect. So I'm not sure where that information came from, but
Okay,
that's not the case. Maybe an older system, I don't know. I don't know.
I'm not disparaging firemen. If I was a fireman, I would probably be worrisome too of getting shocked, but it shouldn't be the case that would ever be a possibility.
Yeah, because it was somebody from within Allegheny County that was basically doing the training, that was a solar expert, shall we say?
That's a shame.
Still in-
Is that an expertise? I don't know.
Well,
So-
it would be true only if they didn't turn the switch off and power is still going to the house. As soon as you disconnect power, all these things shut down because they need
Yeah.
to sync,
Well, it's
they
also
need the
assuming
AC
you
to
get
sync
the
on and they shut off.
Sure.
right, if you're a fire, but it's.
If you can get to, the knife switch is by code, has to be right next to the meter, which is on the side of the house.
There you go.
So unless that's obstructed, which I sure could be in a fire, yeah.
Well, I'm just, wouldn't
The
have
fire
fire
would be outside, not inside, which is. it's perfect.
Anyway, very specific case. I'm gonna hop back into the, I've got a few more things to talk about in the presentation, if that's all right. We'll finish up here. We got a few more.
I'll back down.
Yeah, sorry. Thanks, David. Appreciate it. Yeah, so, so the next thing I want to talk about was some of the pricing. So again, this is specific to my system, but you can kind of see the percentage of costs, right? So you can see that I had some Q-cell 390 watt panels, about 40% of my total costs.
Hey, Tony. You make sure to hit share.
Oh, it's not shared? Okay, sorry about that. Let me share screen. You good now? All right. Yeah, so you can see that there is there's a certain percentage, what was I say, 40% of the total costs came from the panels. Racking system was about 15%. The optimizers on the back of each panel was about 15% of total costs. The inverter was about 17%. Like I said, I sourced all the materials. I did the permitting, I did the drawings. I have a buddy who has a stamp, so he did the PE stamp for me for the permitting process. So obviously my cost was a lot lower than, unless you wanted to try and do all these things yourself. So, and then I did subcontractor, roof subcontractor and electrician. So mine came out to about $15,800, let's say around $16,000, which is about $1.55 a watt. So some of the things you want to consider are your roof angle, roof pitch. Like I mentioned, my roof pitch was pretty steep, and with that metal roof, it was not enjoyable to be up there. So I went ahead and subcontracted out an installer. You also might have to consider trimming certain shrubs or trees depending on the shading. And I know there's a lot here, but this is an image of the pro forma that I'll share with you guys. That Katie will send out an email to everyone. All this really does is just give us an idea of our electricity costs over the life of the solar array. And it also gives us the savings over the life of the solar array, right? And so in this, we don't have to get into too much detail. The blue area are your inputs. So you input things like the electricity production you can get from PV watts. You can input the size of the system. And then there's another tab where you can sort of input your costs, right? So that would give you your cost per watt if you want to do that calculation. And then if you want to take a loan out or anything like that, for what it's worth, maybe I'll talk about this first. I'll talk a little bit about my situation. So anyway, I plug all that in, and in my case, at $15,800 over the life of the panels, I'm paying about 4.5 cents per kilowatt hour. So much, significantly less than half of the electricity rate I was paying before.
And that's going to stay the same.
For 30 years, yeah. Now there's gonna be some degradation, so it's not gonna produce quite as much. Let's say year 30, I might have 85% of that power being produced versus 100% now. So
But you're still connected to the grid.
yes, yeah,
So at times, you are pulling from the grid.
that's right. Yeah.
But what you're putting back in more than compensates for that, so.
Yeah, so my case, not real. So my case, I produce about 80% of my total consumption.
But so is that 4.5 cents also considering that other 20% that you're pulling from?
No, this is just the
Just
the electricity.
Just the
So I'm
electricity
gonna say
generated.
12% on 12 cents per kilowatt hour for anything I pull from the utility.
Okay,
So yeah,
so
that's
this is
still
not
not
a
paid.
total, this
Not
is
a
just
total.
what your solar.
But if I had more space on my roof, I would have sized it larger. I would have tried to go total if I could, right? I didn't want to go on the front part of the roof. My wife would have killed me, basically. That's yeah. So then, you can see the overall savings is around $56,000 if I took out a loan, or if I paid cash, it would be around $58,000. Let's say. So obviously, there's quite a bit of savings. The electricity rate is much lower. And in my case, I actually, instead of, pulling money from savings or something like that, I actually did a home equity line of credit at 4%. So I had zero down, and essentially my monthly payment for my home equity line of credit is about $20 more than what I produce from this. So I pay about $20 for my home equity line of credit, maybe tack on another $10 or so for the additional electricity that I don't produce. So let's say about $30 a month is what I pay, and in 10 years, I'll have a solar array that will produce the majority of my electricity for free at that point, if you want to think of it that way. The other cool thing is you obviously get a tax credit back. So I had $0 out of pocket, and I got a tax credit for a little over $4,000 or something that very next tax season. So I put that in mutual funds, right? But yeah, anyway, so there's some ways to work it that you can take out a loan, obviously if you want to pay cash or something like that. I'm not sure, me personally, I don't think I would suggest considering leasing solar. I know some people do that. I personally probably wouldn't go down that route, but that is another option. So I don't know, this is basically kind of a break-even analysis payback period. So my $15,800 on the upper left little chart there, it basically, if you were to pay cash, the break-even point would be about 7 years. So if you had a fully installed, professionally installed warranted workmanship, warranted monitoring and stuff like that, it's gonna cost you a little bit more. So your payback period might be a little bit longer, obviously. And then on the right-hand side, my loan break-even analysis, I like to say it's infinite, because I paid $0 out of pocket. I know that there's a little negative value there, but I actually ended up paying no down payment at all. So I had an infinite return, essentially, with the solar renewable energy credits and the tax credit that I got back. I basically am never in the hole. So it's kind of a cool system, for me at least. It worked out pretty well. The other thing, and again, I don't know, I think most people focus on the bottom dollar, but there's also to consider the greenhouse gas emissions and how much. So there's the Environmental Protection Agency has some, they have some equivalency calculations. So you can calculate based on your kilowatt hours and your region, you can figure out the amount of carbon dioxide emissions that you're, let's say, displacing by using your solar array versus using the energy mix in your area. So after 1 year, the system displaces about 18,000 pounds of CO2 over the life of it, over 500,000 pounds. And there's also an equivalency to the number of trees that would be like planting, right? So over 30 years, it'd be like planting 4,000 trees worth of carbon dioxide. So for those of you that care about the environmental side, I think those are pretty significant numbers. You can imagine if more of us put solar on our house, we would obviously displace a lot more greenhouse gas emissions. A couple things I wanted to talk about. I think everyone's probably heard of the investment tax credit. This is quite literally a reduction from your income taxes, right? And so the minute the year that your solar array goes on, you can claim that on that year's taxes. And it is 26% through the year 2022, right? So 26% of the total cost of the system will be returned back to you in the tax credit, in the form of tax credit. And then it's supposed to reduce off, from there. I don't know. I guess we'll see what happens in government. But I guess we were all assuming that this 26% would be extended more. Hopefully it does get extended further down the road. So we'll see what happens there. But there's something else. Has anyone here ever heard of an SRAC? This is kind of something you heard of it. Okay. Yeah. So it's something that I don't know if too many people know about this solar renewable energy credit. And so basically it amounts to 1 megawatt hour. So 1,000 kilowatt hours of production. If you remember back when we did our projections, it was something like my house should produce around 11,000 kilowatt hours. That would be 11 megawatt hours. And so each one of those megawatt hours develops a SREC credit that can be sold. So it's like a market system, right? So with that megawatt hour, the market varies, but and you probably can't see this, the little chart on the bottom, the value, let's see, recently, this was in March 22, so a couple months off, was about $40. So you get about $40 back for every megawatt hour that you produce. So in my case, I have, well, it's not perfectly oriented, so maybe not 11, maybe closer to 9 or so megawatt hours that I'll be able to produce and receive $40 for each of those.
Where are you getting the money from?
Yeah, so there's some different companies that have an exchange. So I think it's called SREC Market, and I sign up with them, and they basically are able to see the electricity I produce from my inverter. So kind of like the monitoring system that we were talking about earlier. They can see directly when I produce a megawatt hour, and they'll sell it on the market for the market rate. And I can show you, actually, here's what it looks like. So I took a look at it. For what it's worth, I didn't sign up for this until shortly before October, so I probably missed a couple megawatt hours when I first installed it. But you can see that I was paid, let's see, $37.20 3 times, and then March, it must have went up a little bit. I was paid $38.50. So this goes directly into my bank account, which is kind of cool. So a nice little way to earn a little extra money. And that's all part of the pro forma that I'll share with you guys too. As far as just solar array, that's kind of all I had as far as the solar array itself. I wanted to talk just a couple additional add-ons that I think mesh really nicely with the solar system. The first one is if you're considering an electric vehicle, you can imagine at 4.5 cents per kilowatt hour, your cost of running that vehicle is going to be a lot cheaper than at 12 cents, right? And so the cost to drive an EV vehicle is way less than a gasoline vehicle. just from the energy part, right? Obviously, there's typically a more higher upfront cost, right? EV vehicles are coming down in price, but they're still typically more expensive than an internal combustion engine vehicle. Although I'm kind of excited about that Ford Lightning, that seems pretty neat. Anyway, to go back, so 2021 Honda Civic, let's just say, I looked it up, combined MPG is 32 miles, so to drive 100 miles at today's gas rate, it would take about $15, right? My little Chevy, I have a Chevy Volt, and it's a plug-in hybrid, so it has a gas engine, and it's got the battery, right? So I only get 40 miles on a charge, but I actually end up driving, the majority of all my trips are all battery. So, unless I'm driving a long distance, it doesn't kick over to the gas. So I plug it in every night and charge it up. But to go 40 miles, it takes 10 kilowatt hours of battery. So at 4.5 cents, that means for me to travel 100 miles in my car with my solar array, it's $1.20. So $1.20 versus $15. If you're using the utility rates, 12 cents, it's about $3. So the cost is about 1/5 compared to a gasoline vehicle. And you can imagine as gas prices fluctuate, if they go down, obviously maybe it might be 1/3 instead of 1/5. But the point here is much less cost to the energy consumption of the vehicle. The other thing you consider is with an electric vehicle, mine is a little different. I actually do have an engine in mine because it's a plug-in hybrid. But if you have a strictly electric vehicle, you no longer have whatever oil, the engine oil or transmission oil to change out. You don't have to change out the timing belt and serpentine belt and all that kind of stuff. So you still have brake pads, right? But it has regenerative braking, so your brake wear actually reduces there too. So maintenance costs in general are typically lower for an EV vehicle. I know there's it's very small, very hard to see this a little chart down here, but basically the left-hand side is showing dollars per gallon. And so you can see the red bar is the dollars per gallon. You can see it fluctuating all over the place. And right now we're right around $4 and let's say 70 cents per gallon. The blue at the bottom is just above $1. So that's the equivalent, what they call the equivalent dollar per gallon. Obviously it's an electric car, but it's kind of an equivalency there. So essentially with an electric vehicle, you're pretty steady, right? You can see some fluctuations based on the electricity price a little bit on the blue bar there. So you're pretty steady right around $1 per, $1 per gallon equivalent versus you can imagine anywhere from $2 to $4 or $5, right? So there's quite a big difference. We mentioned this earlier also, the vehicle to grid is another option. I don't know if the technology is really quite there yet, but next 5 years, I think we'll see it. Basically using your car as a battery for your home, right? So if you have a car that can go 300 miles and you only drive 50 miles to and from work, you got an extra 250 miles worth of electricity sitting in it, right? And so you can imagine at night, you could discharge, maybe you don't discharge all of that, maybe you discharge a portion of it, and you charge it back up when the solar is out in the middle of the day, right? And so you can use your vehicle as a charge-discharge battery instead of having to purchase a whole separate unit. So that's called vehicle to grid. There's been quite a bit of research in that area. The other thing is battery storage in general, right? So obviously there are some additional costs in buying batteries, but we can sort of mitigate to a certain degree power outages and things like that. Go completely off the grid if you're willing to spend enough to store the power necessary. And then finally, home equity, right? So like we said before, if I pay the utility company every month, I'm really not ever gaining any dollars in my account, right? Because home equity technically isn't dollars in your account. But if I go to sell my home with a solar array on it, it's going to be worth a little bit more than without it, right? Depending on if you're my wife and she says, I don't know if I like the look of it, aesthetics, no, I'm just kidding. But yeah, so and there's been some studies, a number of studies that anywhere up to about 50% of the cost of the system is typically what you could get back in equity. So right off the bat, you get your equity, you get a tax return, and then over the life of it, you would get solar renewable energy credits. Not to mention, you can have a net metering where you're selling electricity back to the grid and working that way.
So on those energy renewable credits,
Yeah.
you just mentioned lifetime. Do you think these are gonna continue on for years of the energy credits?
Yeah, no, that's a great point. So they're based upon what's called the renewable portfolio standards. That's, I guess, government regulated, that PUC regulated. I don't know if this, I'm not sure if the Congress has to past that. I'm not sure, but it's.
Per state.
It is per state, for sure.
Per state, yeah, so. But there's certain standards, PAs lag behind compared to other states. You can look at a company called SREC Trade, you see what they're worth in other
Yeah.
states, like in Maryland or in the New England is like $300 per range, which is
Yeah.
significant.
Yeah.
But that is the government saying, hey, utilities, you must generate X amount of your generation from renewables. And they say, you can either do that by building a solar farm, or you can buy energy produced by other people, and that's tracked by this credit. So then they say, hey, government, we built this much and then we paid for this much, and that satisfies that mandate.
Good point, though. It is a fluctuating market.
Totally,
right?
yeah,
And it's based on the renewable portfolio standards, but also the demand, right? So if some of these companies start to build their own solar array or something, that the value might go down or whatever.
right.
I just checked New Jersey today, it's $250. That's
Yeah.
25 cents a kilowatt hour.
Yeah.
I mean, to not build solar in New Jersey would make no sense.
The only reason we're not that is PA state legislation. By our, I think the mandate is 0.5% of Pennsylvania's electricity has to be solar.
It's really low.
And if there have been bills introduced that could up that to 8%, and that would send the abstract marketplace through the roof.
Yeah,
But fingers crossed.
yeah.
That'd be great.
Because of that market variability, some people don't even include that income in their pro
Yeah.
forma, right? In their
It's
projections.
yeah, it's
of income. Yeah.
a risk.
Hey, anyway, thank you guys very much. I really appreciate your time.
Yeah, sure.
If you have any questions, I'll hang out.
Yeah,
and
cool.
then, yeah, thank you, David, for coming. For what it's worth, the Environmental Advisory Committee, we do have a speaker series. We'll have another speaker series in September. That'll be on water resources, probably September 22nd, I think.
Yes.
And then throughout the summer, we're hoping to have some nature walks where you can kind of walk and learn, enjoy nature while we have an expert sort of tell us about some different aspects along the trail. So thank you guys very much. I really appreciate it. Thank you. Sorry.